Hello there, and I would like to go ahead and get started with Chapter 5, Sections 4 and 5, and this is all about rational functions. We've already talked a lot about domain and vertical asymptotes. We're going to get into a couple of other things, but let's just kind of review about what to do when they ask for the domain of a rational function. Remember, a rational function has a numerator and a denominator. And what I want you to do before you do anything is factor everything that you can. So in this example, this is my rational function, and I'm going to take that denominator right here, and I'm going to factor it. And from the factor, I know that I cannot have any zeros in the denominator. So this binomial, x minus 3, I'm going to say cannot equal 0. So I know that x cannot equal 3. From this binomial factor, I know that x cannot equal -2. And we've talked about that already. So that's a little review. So let's put it together. We discussed this. So if I graphed this, I would see that the graph is not going to be at 3 or at -2. That's because there are vertical asymptotes, chopping the x-axis at 3 and another chopping the x-axis at -2. So if they ask for the domain, you're going to tell them x cannot equal 3 or x cannot equal -2. You might have to put it in interval notation. If they ask for the vertical asymptotes, then you say at x equals -2 and x equals 3. And MyLabs Plus will tell you how they want you to present your answer. So I have this graph right here, kind of nice. I'm going to keep working with this graph. So to find vertical asymptotes, you set each factor in the denominator equal to 0, and then you solve for x. So new function. I'm going to take my denominator, I'm going to factor. I'm going to talk about domain, and I know that x cannot equal 3, x cannot equal -3. I set up my intervals if they wanted an interval notation. And I know that my vertical asymptotes are at +3 and -3. And now let's move on to something new. To find the horizontal asymptote, you're going to look at the original function, and we're going to compare the degrees. And we've got two situations to deal with. If the degrees are equal, I'm going to have a horizontal asymptote, chopping the y-axis at some number. I'm going to take the lead coefficient of the numerator over the lead coefficient of the denominator. And that's only when the degrees are equal. The second situation is when the degree of the denominator is bigger, then your answer is just flat out y equals 0. The x-axis is the horizontal asymptote. Let me clarify this by looking at 3 examples. All I'm going to look at is the lead term. Nothing else matters in horizontal asymptote world. So on this one, the degree of my numerator is 1. The degree of my denominator is 2. Since the denominator is bigger, y equals 0 is my horizontal asymptote. Example 2, the degree is 2 on top, the degree is 2 on bottom. So here, this is the case where the degrees are the same. So I'm going to take the lead coefficient of 4 and put it over the lead coefficient of 1. 4 divided by 1 gives me 4. So I would have a horizontal asymptote chopping the y-axis at 4. In this third example, I'm looking at the highest exponent. My degree is 3. Down here, my highest exponent degree is 3. This is another case of degrees are equal. So I'm going to take coefficient 6 over the coefficient of the lead. Well, actually, this is the lead because it's the highest exponent over -8. 6 over -8. And if I reduce that, I'll have a horizontal asymptote chopping the y-axis at -3/4. So let's put some things together. In this example, I factored my denominator, my domain, x cannot equal -1, x cannot equal +1, because there are vertical asymptotes there. And you can see on the graph my nice little vertical asymptotes. Oops. Okay, the horizontal asymptote. Remember, look at the original. The degree on top is 2, the degree on bottom is 2. So I will have a horizontal asymptote at 3 divided by 1. Chop the y-axis at 3. Pretty easy. Another example, I'm going to factor my numerator. I'm going to pull out the GCF of 2 and continuing factoring. So you have to spend quite a bit of time factoring. My domain, remember the denominator cannot equal 0. So x cannot equal -2, x cannot equal +2 because there are asymptotes. Domain talks about where the graph is, where this blue graph actually is. Horizontal asymptotes talk about where the dotted lines or the imaginary lines are going to be. Now my horizontal asymptote, I'm going to come back to my original. Degree on top is 2, degree on bottom is 2. Lead term, lead coefficient over lead coefficient. My horizontal asymptote chops the y-axis at 2. The next thing that you're going to have to work on are the intercepts of a rational function. And this is a review also. To find your x-intercept, substitute 0 into y and solve for x. To find your y-intercept, substitute 0 into x and solve for y. Or some of you probably just want to put it in your calculator and find your intercepts that way. However you want to do it, the easiest way for you, that's the best way. So let's put it all together. So our steps, number 1, make sure you factor. Write in lowest terms, and I'll talk about lowest terms in a little bit. Determine your vertical asymptotes and your domain, they kind of go together. Determine your horizontal asymptote. Oblique asymptotes, I will talk about that later also. Determine your x-intercepts and your y-intercepts and get a good graph on your calculator. So let's take a look at this function. I pulled this off of the quiz on MyLabs Plus. So some of you may see this again when you take that quiz. So I factored my denominator. And I can tell my domain is going to be x cannot equal -5 and +4. Have a little fancy notation there. My x-intercept, I decided to do that. I looked at my graph and I did my intersect and I found my x-intercept was at 0. And remember, when your x-intercept is 0, your y-intercept is 0 also. My vertical asymptotes will chop the x-axis at +4 and -5. For my horizontal asymptote, I'm going to go back to my original and notice the degrees are the same. So coefficient of 1 over 1. So horizontal asymptote chops the y-axis at 1. And there is no oblique asymptote. Oblique asymptotes and horizontal asymptotes, you can't have both. If you have a horizontal asymptote, you will not have an oblique asymptote. Oblique means slant. So let's talk about these asymptotes a little more. So warning, a function will never touch or cross a vertical asymptote. It gets closer and closer and closer, but never touches, and it goes up to infinity, or it will get closer and closer and closer and go down to -infinity, one or the other. As it approaches, the function will approach +infinity on one side. In this case, let's look at this asymptote. On one side, the curve will approach +infinity, and on the other side, it will approach -infinity. For this asymptote, same thing. On one side, it approaches positive, and the other, it approaches -infinity. Because the multiplicity of each binomial is odd. When the multiplicity is odd, then the asymptotes will go in opposite, the curves will go in opposite directions. Now, a horizontal asymptote. This is kind of cool. A function may sometimes cross a horizontal asymptote. So, on this example from MyLabs Plus, they're going to ask you determine the points at which the graph intersects the horizontal asymptote. Okay, what I did, I put my graph in y sub 1. I had it there anyway because I wanted to see what the graph looked like. And in y sub 2, I have the horizontal asymptote of 1. And I did intersect. Second calc 5, enter, enter, enter. And it gave me an error message. And you guys know that when that gives you an error message, your screen is not big enough. So I changed my window, and I think I went something like -50 to 50. And I intersected again, and I found that this curve, this blue curve, is actually touching the horizontal asymptote way down here at the point 20, 1. Finally, the last item we must find is a hole. Sometimes rational functions have little holes in them. And this is going to occur when there's a binomial factor in both the numerator and in the denominator. Let's look at an example. So I took this function and factored it. And look at that. I have a binomial factor of x minus 1 on top and on bottom. I'm going to go ahead and cancel those binomial factors out. And I'm left with this function right here. Okay. So my domain, however, still has to come from this function up here. Whoops. So my domain, x cannot equal +1, x cannot equal -5. But my vertical asymptote and everything else comes from this new function right here. My vertical asymptote chops the x-axis at 5. My horizontal asymptote, of course, we always have to go back to the original, and that's going to be 1/1. Now this hole, what we have to do to find the hole is take one of those binomials that we canceled out, set it equal to 0, and we're actually going to have a hole at x equals 1, okay? So right about here at x equals 1, there's going to be a little hole in the graph. The x-intercept was -3 and the y-intercept was -3/5. But what I'm concerned about is, how do you find a hole? You set one of the binomials that you canceled out equal to 0, and that's going to tell you where to find your hole at x equals 1. So I'm going to go to 1, and there'll be a little hole right there. So this oblique asymptote. An oblique asymptote is actually a slanting asymptote, and that's going to occur when the degree in the numerator is greater than the degree in the denominator. And the asymptote is going to be a line when the degree is 1 greater than the denominator. But because of time, we're not going to be working with oblique asymptotes. Just too much is going on in our lives right now. So I kind of crossed that out of the homework and the quiz. And just remember, you cannot have a horizontal and an oblique. Okay, so sometimes they'll ask you, is there an oblique? And you have to say, if the top is greater than the bottom, yes, there is an oblique. But you're not going to have to find it for me. And that's it. And I hope that this has helped you guys a little bit with rational functions. I combined section 5.4 and 5.5. And good luck.